that's the point of this analysis. Okay, so we analyze the 2 points. So these things are often called asymptotic analysis. Okay, so this is just for your benefit, not for this course, but I mean, you might actually come across this asymptotic analysis, but asymptotic analysis. Does an asymptote mean? Asymptotes are like this tends to infinity. So what happens if you make something very, very large? So this is generally when you're trying to do some analysis like this. You have some circuit, you know its output, you're trying to make some parameter extremely large. What happens at that extreme point? There is no extreme point. You can go far larger and larger and larger. So you tend to infinity. What happens? So these are called asymptotes. So these asymptotes, this sort of analysis is called asymptotic analysis, basically. So we do an asymptotic analysis of this filter, and we see that if I make the frequency very large, my output would become almost equal to the input, because h of j omega is the scaling, and the scaling becomes 1. Okay, so all right. So next is obviously this plot. The next is obviously this plot. So these are asymptotes, but what about the entire plot? So if I try to plot the 20 log 10 of h of j omega against omega, then we will see a curve like this, the one shown here. Okay. So if you have a very large frequency, then h of j omega in dB would be 0, because h of j omega is 1. So log 20 log 10 of that is 0. So you start at 0 and you slowly decrease the frequency. So as you come down in the frequency, so you are basically coming down, getting smaller and smaller. So that's basically the idea. So okay, so that's the point. So if you plot this is clearly a high pass filter. So low frequencies are greatly diminished. High frequencies are very high frequencies are passed almost unaltered. So that is why this is called a high pass filter. So and then what is the 20 to 3 dB cutoff frequency of this filter? So you take this r by omega l whole squared plus 1, and you set this thing to 2. So this thing inside is 2, which means the whole thing is square root of 2. Then using the same logic I gave a little while ago, so if I can make this denominator square root 2, this whole thing square root 2, then for that value my h dB will be minus 3. Okay, so for this 3 dB cutoff frequency omega c, my denominator should be equal to square root 2, which means this thing, just a moment, so this should have been squared. If I solve this, I get this thing. So r divided by omega cl whole square plus 1 is equal to 2, which means omega c is equal to r by l. Okay, this omega c is r by l. So again, if you see, this is nothing but 1 by the time constant, because the time constant is l by r. That has got nothing to do with the filtering behavior. The time constant is 1 by r. So this is still equal to this thing is still equal to 1 by the time constant. So basically, it's the same cutoff frequency, but the difference is that we now have a high pass filter. So what does it mean? What is the main takeaway from this discussion? So of course, if you take this RL filter and then you take the output across the R, you have a low pass filter. If you take the output across L, it's a high pass filter. So that's a very important observation. It says that given a circuit, unless you are told what the output is, you can't tell whether it's a high pass filter, low pass filter, band pass, or band reject, because it depends on where you are taking the output. So if I am suppose given some arbitrary circuit like this one, and I'm asked what kind of filter is this? Well, I don't have an answer to this question because I don't know where the output is. You need to ask, what is your output? Is it across the this resistor? Is it across this inductor? Is it across this capacitor? What? So that question we need to ask. Unless we know that, you will never be able to answer this question. So specifying exactly where the input is and where the output is important, and just saying that RL filter is a low pass filter, because people tend to say that RL filters are low pass filters. What they really mean is that it's an RL circuit with the output taken across R, not across L. Because if you take the output across L, then it's no longer a low pass filter. Okay, so this is something we need to keep in mind, because this is important. So whenever we are talking about a filter, we need to ask where the output is. Okay, so this is important. And then okay, so basically we are done with RL. So any questions regarding RL circuits? Okay, so if not, let's move on to the next topic, which is the RC circuits. So what happens with RC circuits? So RC circuits are just like RL circuits, but you replace the L with the C. So you have a circuit where you have a voltage source just like before, then you have some capacitance, and then you have a resistance. Okay. So now if you take the Laplace domain, I'm not going to go into these details because we don't need them. I'm just giving it for your information. So you have a input signal, then you could replace C, the impedance of the in the capacitor in the Laplace domain is 1 by SC, and then the resistance remains R, nothing changes. And then what we're really interested in is sinusoidal inputs with frequency omega. So sinusoidal with frequency omega. So this is what we're really interested in. So if that is the case, so basically sinusoidal frequency omega. And whenever I talk about frequency, I talk about angular frequency, not the Hertz frequency. Omega is equal to 2 pi f. I'm not talking about the f, but about omega, about 2 pi f. Okay, so this is your sinusoidal input with frequency omega. So if that is the case, then what happens here is, just like you replace the capacitor inductor with j omega L, you can replace replace an inductor with j omega L, you can replace a capacitor with 1 by j omega C. So that your inductor, so the main thing here is, so if you take an inductor, L becomes j omega L. For C, it becomes 1 by j omega C, which is also equal to minus j by omega C. So you will replace it by one of these two. Okay, so you could have either 1 by j omega C, or you can write minus j omega by omega C. But the point is, the impedance, when you are trying to do this impedance analysis, you just replace the inductor with j omega L and replace the capacitor with either 1 by j omega C or minus j omega C. Anyway, so this is, so that actually gives you this particular circuit that you can see on the slide here. So the input signal is supplied to a circuit with an input impedance which is equal to R plus 1 by j omega C. So what is the current here? Again, exactly like resistive circuits, you take the voltage, input voltage divided by the total resistance. In this case, it's the total impedance. So you divide V in divided by R plus 1 by j omega C. So so we have V out is equal to I times R. Again, same as before, you have a current flowing through a resistor. So the voltage across the resistor would be I times R, and then voltage across the resistor is our output as well. So our output voltage V out is IR. And so what is I? I is, as we just found, V in divided by the total impedance, which is R plus 1 by j omega C. So V in R divided by R plus j omega C, and that makes it V in R divided by R minus j by omega C if you wish to write it in the second form. So I just moved it from j omega C. So the 1 by j omega C, I made it minus j by omega C. Okay, so it makes it easier to have the j in the numerator. That's why I did this. Okay, so now coming to this next point. As before, we are interested in this function h of j omega. And what is h of j omega? H of j omega is output by input, and output by input is, from the previous equation, we can readily say that output by input is R divided by R minus j by omega C. So this is your h of j omega. So again, the point number 3 is, after this point, we wish to find out the magnitude of h of j omega, because that's our scaling, because that's what actually determines how much we suppress or amplify an input. So h of j omega is magnitude of V out divided by magnitude of V in. And what is the magnitude of V out? I mean the magnitude of the numerator, that's just R. So magnitude is also R, because R is a real number, and the denominator becomes square root of R squared plus 1 by omega C squared. So this is the denominator. And then we simplify this a little bit. After we do the simplification, finally we come to this expression: 1 divided by square root of 1 plus 1 by omega RC whole squared. So that expression, we can now do an asymptotic analysis. So first question is, what happens if omega is 0? So if you make omega equals 0, then you have in the denominator 1 plus 1 by 0, which means we have 1 plus infinity. So you have 1 divided by square root of infinity, which is nothing but 1 by infinity, and that tends to 0. So basically, if you make omega equals 0, then you get a 0 at the output, which means you have a DC input, gives you no output. So this means, so DC input, so basically this means DC input, 0 output. No matter what the input to voltage of the DC is, the DC input will give you 0 output. Okay, so next you make omega very large. You make omega tend to infinity. So basically you make h of j omega, you take the limit of omega equals infinity. So basically limit omega goes to infinity, 1 by 1 over actually j omega. So basically omega RC. So this thing you can easily show that it goes to 1. So for very large values, it is 1. So very high frequency, no scaling. Very high input, very high input frequency, no scaling. Okay, so basically what it means is no scaling or very high input frequency, no suppression, no suppression. So what you do is, if you supply a very high input frequency, then there is no suppression of the input. So whatever you apply the input, you see that at the output. So that's the point. And then if you plot these things, you'll see this graph as expected. You'll see something like this, and then you can find out what the omega C is. So this, the value at which HdB becomes -3 will be the omega C. And what is omega C? Now, if you want to find out, omega C you would find if you make this term, this denominator, so this denominator, if you make it square root 2. So in order to make it square root 2, what I have to do is, in order to make it square root 2, I have to make 1 plus 1 by omega C RC whole squared is equal to 2. So if I make it 2, then I can solve for omega C, and that would be 1 by RC. And now, again, without proof, without any derivation, I am stating that the time constant of an RC circuit, like the one I showed here, is equal to tau equals RC. So again, what we see here is that the 3 dB cutoff is 1 by the time, 1 divided by time, the inverse of the time constant. So this is again another point. So basically a time constant, if I told, as I have told before, time constant actually tells you how quickly or how sluggishly a circuit responds to a step input. You suddenly apply a voltage, high voltage to the circuit, there was nothing in the circuit, you suddenly apply a high voltage. How quickly the output voltage increases and reaches its final value. So that how quickly, that to answer that question, you have to refer to the time constant. So a circuit with a small time constant will react very quickly. Circuit with a large time constant will slowly react. But in this concept, we have seen that a larger time constant, the time constant tells you what the 3 dB bandwidth is. So the larger the time constant, the smaller the 3 dB bandwidth. 3 dB bandwidth, not 3 dB cutoff, I'm sorry, 3 dB cutoff. And the smaller the time constant, the larger the 3 dB cutoff. Okay, so this is one point. So what I suggest as a practice problem is to try out the same RC filter, but with output taken across C. So just like we did for the inductor. So now, instead of taking the output across R, so like here we are taking the output across R. So we did this analysis assuming that I am connecting a voltmeter across the resistance, and then I am getting some output. What if I connect the voltmeter across the capacitance? What output will I get? So that question you try to answer using on your own. I mean, do analysis and see what the output would be. The output should be this time. You should get a low pass filter. So essentially, if you have any two element circuit with two element, either RL or RC, you take the output across one, you get some type of filter. Let's say it's a low pass filter. You take the output across the other element, you should get a high pass filter. It's always that case. That's because if you think about Kirchhoff's voltage law, so if you think about KVL, what's happening here is that the voltage that appears across some place and across the inductor and the capacitor and the resistor, or the capacitor and the resistor, these should sum to the input voltage. Now, if the output is 0, that means there is no voltage appearing across the resistor, for example, which means all the voltage should appear across the capacitor or the inductor. So if it's a low pass filter, when you're taking the output across the resistor, that means low frequencies are not appearing high frequencies are not appearing across, high frequency voltages are not appearing across the resistor. So they must appear across across the capacitor or the inductor. Otherwise, Kirchhoff's voltage law will not be satisfied. So even without doing the analysis from scratch, you could say that if this is a low pass filter, if this is a high pass filter, this circuit right here is a high pass filter, then I will get a low pass filter if I take the output across the capacitor. So this is something you could easily tell. Okay, so this is something, but I would like for you to try out this analysis. So this is a practice problem. Okay, and then this is fine. So we have now covered both RC, RL, low pass, high pass filters. So basically we now know everything needed to analyze these RC and RL circuits. Now finally there could be RLC circuit. So the same circuit will have both L and C. I am not going to go into detail for this circuit. I am just going to show you the basic analysis procedure, which is exactly the same. So all you have to do is, suppose I am taking the output across R. So the V out would be just I times R, where I is the current flowing through the circuit. What is I? I is nothing but the voltage, input voltage divided by the, so let's call it V in, V in. So input voltage divided by the total resistance. What is the total resistance? The total resistance, total impedance is j omega L plus 1 by j omega C plus R. So that's your, just sum up all the resistances and reactances, and then you do the analysis. So I just write it down that this is sinusoid with frequency omega. Okay, so this is important again. So because these things don't apply if you have something else. But why? So you might ask, why just sinusoid? Why focus so much on sinusoids? Why not? What happens if you have something else? The point is, if you are able to do this analysis, then you can generalize it to other circuits, because you might have taken some courses in mathematics where they taught you Fourier transform. I don't know how much of that is actually apparent to you in that mathematical course, but at least it was not very clear to me when I was an undergrad and I tried to take these courses. But the point was, the entire idea behind Fourier transforms is that you can take any arbitrary signal and express it as a sum of sinusoids. So basically, if you have a square wave, you can express it as a sum of sinusoids. If you have some other triangular wave, you can express it as a sum of sinusoids. Any arbitrary signal can be expressed as a sum of sinusoids with varying amplitudes. So different frequencies, so you'll have some sine omega 1t plus sine omega 2t plus cos omega 1t, cos omega 2t, something like that. And each of them will have some separate amplitude. But by virtue of the superposition theorem, you could analyze each of them separately and then add up the input, add up the final outputs. And that will be your complete output, the aggregate output. That's why it often suffices to analyze just sinusoidal input and not look at larger input. And then when you actually need to do something for a larger input, you just take the take help of Fourier transform. Okay, so that's the idea. But right now we only care about what happens to a waveform with a certain frequency, because that's our main goal, right? We want to find out if I have a high frequency input, is it suppressed or is it not? If I have a low frequency input, is it suppressed or is it not? So that's the question we are trying to answer, and for that, all we care about is sinusoidal inputs with certain frequency omega. Okay, so coming back, you have this circuit, RLC circuit, and you want to find out what I is. And I is nothing but V in divided by R plus j omega L minus j omega C. And that is nothing but this particular expression. After some simplification, I took j out. So I express it as x plus yj, kind of a typical complex number representation. And then I can find out V out. V out is nothing but I times R. So I is already given here, V in by this term. So V out is IR. So that will be V in times R divided by this denominator. So from there I can find out V out by V in, which is h of j omega, which we have defined as h of j omega. And that is R divided by this term. So there is this ratio of complex numbers. And then finally, we are able to find out the magnitude of h of j omega. So R divided by 1 by R divided by square root of R square plus omega L minus 1 by omega C whole square. So if you take this and then you take out R, and then you finally result in this expression on this on the screen. So this expression you will finally see. And then if you actually try to plot this, you will see that you will have a plot like this, something like this. It's a little hard to do this asymptotic analysis over here because there are two dependencies. So omega L by R minus 1 by omega R C. So basically omega appears in the numerator and the denominator, so it gets a little hard. But the point over here is that if you plot this, you will see something like this. So there will be a peak at some point. There will be a peak at this point. So this thing is actually called the center frequency. Center frequency of the filter. This is also equal to the resonant frequency. So if you remember from your previous classes, maybe from at IIT Bhubaneswar or in the +2, RLC filters have a resonant frequency. So in our resonant frequency is the frequency at which the filter provides the minimum amount of impedance. Actually, at that point, this L and C stops playing a part. It's such that each of they cancel each other out. Their effects cancel each other out. So finally, you get a circuit which is as good as just having one resistance. So at that value, you get the maximum output, and that maximum output is occurs at the resonant frequency. So basically, this is the resonant frequency omega. So in this case, we call it, oftentimes we call it the center frequency FC, but yeah, let's not get into all these things. But the point is, after that omega frequency, so this is the maximum frequency, this is 0, let's say, and this is -3. We're talking about dB, okay, again, otherwise 0 doesn't mean anything in the linear scale, so it's dB. So if you have 0 and if you have -3, the point at which it reaches -3 is the omega C1 or upper cutoff frequency, upper cutoff frequency. And then the point at which, sorry, this is not upper, this is actually lower. Okay, this is actually omega C1. Okay, so this is omega C1, this is correct, but this is called a lower cutoff frequency. Lower cutoff frequency. And this term, another omega C2, this term is called the upper cutoff frequency. Okay, so basically you have these two frequencies, as I said before. For a band pass filter, you have two frequencies, and then there is a center frequency, and this is nothing but the resonant frequency. Okay, so this is what you get. But the important point to keep in mind right here is that if you have a RC filter like this, this will give you a this will give you a band pass filter. So the band pass filter, it will have some peak. The response will have some peak, unlike the low pass and high pass filters. Here you will have some peak, and then around that peak would be the center frequency of this filter, and then there will be a bandwidth pass band. So from to lower cutoff frequency and higher cutoff, upper cutoff frequency, these are all again 3 dB frequencies. We are talking about 3 dB. And then there are ways to find out expressions for what omega C1 is and what omega C2 is. I am not going to go into these things unless we need it for some future class, because I don't want to overload you with these things. But this is your band pass filter, okay? And then you could actually derive a band reject filter by taking the output across L and C. So basically you change the output, you take the output instead of R, you take the output across the combination of L and C, and that will be a band reject filter. And then I'll leave it to you to see what happens if you have if you're taking the output across just L or just C. So that's another question. So that you will see, you can do a MATLAB simulation and see what happens over there. All right, so that actually concludes our discussion of this series RC, RL, and RLC filters, essentially low pass, high pass, band pass filters. The reason we discuss this thing is, in the future classes, we will be designing electronic filters. So electronic filters will have more components, not just this RC and not just RL and C. You'll have more stuff. There might be diodes, there might be BJT, MOSFET, all this stuff. And then why do we add these things? They'll give us certain benefits. We will see that later. These are passive filters. One disadvantage of these filters is that they cannot do any amplification. So as you have seen, h of j omega, the maximum value of h of j omega, if you take the h of j omega, so if you take h of j omega, it is always, let's let it here. So in all these filters, if you see, h of j omega is less than equal to 1. It never exceeds 1. It's because in order to have h of j omega greater than 1, you need to have some amplification. Amplification cannot be done by these RLC components. So these are called passive filters. What we might want is active filters. For active filters, you might have h of j omega greater than 1. So that means that circuit is doing some amplification. You are supplying a 5-volt input, 5-volt sinusoid, 5-volt peak-to-peak sinusoid, and you are getting a 10-volt peak-to-peak sinusoid. So it's a amplification with a factor of 2. So therefore, to do that thing, you need to have some extra components, and then we will be learning all these things later. But this one actually lays down the base for the more sophisticated circuits. Okay, so let's. Do you have any questions on this thing?
Band pass filter.
Sorry?
Band pass filter, will that omega C, omega C1 and omega C2 just correspond to minus 3 dB, or can we define it on ourselves?
Yeah, so normally we talk about this minus 3 dB. You can definitely define it as something else, but this minus 3 dB cutoff is the most common. So if somebody just says cutoff frequency, then they're probably very likely 99.9% of the time they are referring to 3 dB cutoff. But yes, these cutoff frequencies are somewhat arbitrarily defined. So you could make it minus 6 dB cutoff, fine. But if you are doing that, we have to be very careful to specify that. If you don't say anything and just say that, okay, my cutoff frequency is 10 hertz, then most people will assume that you are talking about the 3 dB cutoff. If there is something else, then you will have to be very clear in defining that. And for ideal filters, it's easy. Cutoff means cutoff. At that point, everything is cut off. Whereas for these filters, the most common definition is this 3 dB cutoff. But as you asked, I mean, this is perfectly fine. You could actually define it as some other cutoff frequency. Okay, so that's how you deal with these things. But normally we are talking about 3 dB cutoff. Yes. Anything else? Okay, so if there's nothing else, then I think we can conclude this session now, and then we will meet in the next class. Next class would be for you this SMS section on Tuesday. So that's it, and then anything else. So I think there are a total of 111, 112. So we have sufficient. So I think everybody attended, everybody got to know, which is nice. So I hope nobody is waiting for the other group. So let's stop here. If you have any questions, feel free to send me an email. And then again, we will meet on Tuesday, and we will also discuss within the next week some of the important problems from the practice problems that I gave you before. And we will try out our hands on MATLAB so that you can plot these transfer functions, plot these frequency dependent behavior. So h of j omega magnitude in dB, so h dB, we will try plotting and see how things change as you change the resistance value or the inductance value or the capacitance value. Okay, so that's it for today. So let's stop here. Okay, and you all have a nice day.